This is video 38 in the lectures on the design of reinforced concrete beams. This lecture is part 2 of the overall design of a beam and deals with the shear force and minimum reinforcement. In video 37, we started to give some dimensions to the beam, the center beam in the living room. We found that for strength, a beam of 660 times 350 millimeters will be okay. And we started with the assumption that the stirrup diameter was 10 millimeter. The tension reinforcement was for diameters 25 and the concrete cover 40 millimeters. The load in ULSP was 52.79 kilonewton per meter and the bending moment 401 kilonewton meter. Within diameter of the shear force of 10 millimeters, of the stirrups of 10 millimeters, the effective depth is 597.5, and we use cotangles theta 2 because the larger the cotangles theta, the least stirrup reinforcement we need. D cotangles theta is then 1195 millimeters. The shear force in function of the local coordinate S of the system is then given by this classic formula. The maximum shear force at the face of the support, that means S is 0.1 meter, is then 201 kilonewton. The maximum capacity of the compression strut is given by this formula. Nu equals 0.53 and FCD is 20. Remember, for shear force alpha CC is 1, not 0.85. And VRD max, if we put in the numbers, is then equal to 795 kilonewton, which is bigger than the VED max of 201. So the compression strut at support is okay. Then we look at the first crack. This is at the distance S equals to 0.1 plus D cotangles theta is 1.295 meters. VED, the shear force at that point, is 138 kilonewton. We look at the second crack. It's D cotangles theta further on, and that's 74 kilonewton. Now, if you visualize it, this is the beam. This is the face of the support. This is the system line. This is 0.1. This is the shear diagram. So we have 0.1, half of the support. Then D cotangles theta further is 1.195. And this is the first crack, second crack. Then you will see at the face it's 201. We compare that with VED max. For the first crack is 138 kilonewton and the second crack 74. Then we look at the capacity, the shear capacity of the concrete alone. The longitudinal reinforcement is 4 diameters 25 divided by the width 350 and D, the effective depth, gives me 0.0094. CRDC is 0.15 divided by gamma C, and K factor is just 1 plus 200 plus the square root of 200 divided by D. It's 1.5786. We plug in the different numbers and we find that the shear capacity of the beam, of the concrete itself without shear reinforcement, is 121 kilonewton. We first check the minimum value is 80 kilonewton, so we must take the maximum of the two. So it's 121. This means that we have to look at the VED1, the shear force at the first crack, and the shear force at the first crack is 138, which is bigger than 121, so we need shear force reinforcement. For the second crack, it's okay. It's only the minimum reinforcement is okay. Then we look at the minimum stirrups. Rho min is 0.08 square root FCK divided by FYK is 0.876, 10 to the power minus 3. The definition of the stirrup density, we put in rho minimum and we calculate ASW over S and we have 0.307. We look at the minimum spacing of the legs, it's 0.75 D or 448 millimeters. ASW over S equals this. It means that we started, remember in the beginning, we started with the diameter stirrup of 10 millimeters. We calculate now with 10 millimeters the distance, the spacing between the stirrups, and using this formula, and we see that the distance is 512 millimeters, which is more than the 448, which is the maximum. So in fact, it means that this diameter 10 is too high because we need a too large spacing. You can now stay with diameter 10 and use, for instance, 450 or something like that, or 440 as spacing. But this is a little bit waste of reinforcement, so we need to lower this diameter. So we take diameter 8, we calculate the distance again, it's diameter 8 every 327 millimeters, so that's okay. So we round it off to the lower side, so we will take diameter 8 every 320 millimeters with 2 legs as minimum shear force reinforcement. The shear capacity of the minimum shear reinforcement, we calculate the effective depth with the diameter 8 instead of 10. We calculate the capacity of the minimum shear reinforcement, which is just the shear reinforcement times the lever arms times FIWT times 2. That's all we have to do. And we have 147 kilonewton. So this means that the minimum shear reinforcement can take 147 kilonewton, which is bigger than VED1, which is 138. So everywhere in the beam, we put minimum reinforcement and it covers the shear capacity. But now we have a small problem in the sense of we have diameter 8 instead of 10. In the previous video, we worked everything out with a diameter 10 because we didn't know what diameter it should be. The difference is the effective depth. So now we have a bigger effective depth than what we calculated before. So the difference now is in favor of the resistance. So we will not redo all the calculations because the difference is first really small and it's in favor. So we'll keep it this way. But from now on, we always calculate with a lever arm of 599.5 because now we know it's a diameter 8. Additional tension in the tension reinforcement due to the shear force, delta F is half VED times cotangent theta. It means 138 kilonewton. We divide by the yield stress of the steel and we have an additional of 317 square millimeters. But now there is an upper limit to this force given by this equation. MED is then 222.5 kilonewton meter. It means that delta F is then MED max divided by Z minus MED divided by Z gives you 331 kilonewton. So delta F 138 kilonewton is okay because the maximum is 331. Additional reinforcement is then 317 square millimeters. Reinforcement for the bending moment at the point of the first crack. So where MD was 222.5, the reduced bending moment is 0.104, and with the use of the tables, we calculate the reinforcement, or we calculate the Z, the lever arm Z. We calculate the reinforcement is 910 square millimeters that we need to take the bending moment at the first crack. But we need for shear reinforcement 317, for bending 910, together it's 1227, and we have put everywhere 4 diameters 25, so that is okay. Now we go to the minimum reinforcement. We are going to calculate the minimum reinforcement for crack control. Sigma S, so it's 500 megapascal, so we do not put a limit to the crack width when we are calculating minimum reinforcement in this case. The K value is 0.75, Kc for bending is 0.4, and FCTF is FCTM, the mean tensile stress in the concrete, and it's 2.9. ACT for bending is half the section, so it's 115,500. And if you put in the numbers, we have 200 square millimeters. So as minimum reinforcement for crack control, we need 200 square millimeters. We now just look at the minimum reinforcement for brittle failure. This is the formula we use. This is the coefficient, the mean tensile stress divided by the FAK times the width and times the effective depth gives us 316 square millimeters. But there is also a minimum about it, which is 0.13% of the section. It's 273. So the minimum reinforcement that we have to provide will be 316 square millimeters. Or this can be done by 3 diameters 12. This means that for the bottom of the section, in the tension zone of the section, in the middle of the span, we see that 3 diameters 12 is okay because we have 4 diameters 25, so that's already all right. But for the top, in the compression zone, we put there the 3 diameters 12 in the compression zone. This is just to protect the beam against brittle failure that can happen due to accidental loads or temperature loads or whatever. So this is the compression reinforcement is the minimum reinforcement in this case. And then we have technological reinforcement on the flanks, because you should keep the clear spacing between, or the center to center between 2 reinforcement bars should be less than 300 millimeters. So this was part 2 in the overall design of a reinforced beam. And next lecture, we will handle the stress check and calc width in SLS. See you next lecture.